Hey everybody, today we're going to do a very brief introduction to a type of transistor called a MOSFET. I'm Michel Maharbis.
And I'm Vivek Subramanian. Let's get started. In a previous section, we discussed another type of transistor called a bipolar transistor. Today we're going to introduce the transistor that is by far the most important transistor in modern electronics, and that is what's known as the MOSFET, or metal oxide semiconductor field effect transistor. So this transistor works a little differently than the bipolar transistor. We won't get into the details of how it operates, but let's look at some of the characteristics that it exhibits. A MOSFET has three main terminals that we care about: the source, the drain, and the gate. Now, what's kind of interesting about a MOSFET is it turns out the gate is separated from the drain and source by an insulator. Michel, does that give you any hints about what the input resistance looks like looking into the gate?
Yeah, so I'm thinking, if there's an insulating sheet between the gate and the other two terminals, the input resistance must be very high and possibly even infinite.
Yeah, that's true. Now, that's in fact, we use these devices in modern op-amps to give us that tera-ohm resistance that I told you about at the input. Okay, so that's basically what we use a MOSFET for, and it turns out the MOSFET is basically a voltage-controlled current source. In other words, the current that flows between the drain and source lines depends on the voltage applied on the gate. The characteristics are somewhat complicated. It turns out it has various regimes of operations. Specifically, when the gate voltage is really low, below some critical value, the MOSFET essentially looks like there's no current flow. In other words, it looks like a really high resistance between the drain and source, and there's no current flow.
So that's like almost like a valve. If VGS is very low, IDS, no current can go through IDS, and maybe it looks like an infinite resistor or something.
Yeah, it looks like a switch. Exactly.
Right.
That's
okay.
right. So one way to think about a MOSFET is to think of it as a switch. But it also turns out that the current that flows from the drain to the source, I told you it depends on the gate voltage, and it turns out there is a dependence on that as well. In other words, if we look at a plot of drain current versus drain to source voltage as a function of gate voltage, we find that the current changes as gate voltage changes. Now, I've put this x-axis as VDS, or drain to source bias, and it turns out there's a reason for that. At very low drain to source biases, the MOSFET current drops off even though the gate voltage is held constant. And so we see that there are therefore three regimes of operation that we can speak of. There's the regime where the MOSFET is off, which is down here.
That's for VGS being very small no matter what else.
Correct.
Okay.
And then there's a regime where the MOSFET is on, and it looks like the drain current pretty much only depends on gate bias and doesn't depend on drain bias.
So in that case, what you're saying is, as I change my VGS, for high VDSs set at this VDS output, the current just jumps with VGS. So if I've got 1 volt VGS, I got 2 milliamps. If I turn my VGS knob up to 2 volts, I suddenly have 4 milliamps running to the transistor, and then 3 volts gives me 6 milliamps, and they're all running through IDS.
Right, and you'll notice one neat thing about this is in this region, to a large degree, the current does not depend on VDS. It only depends on VGS.
So that's why you're saying that in some cases it can look like a voltage-controlled current source.
Exactly, because now the current through here does not depend on VDS, it only depends on VGS. So in fact, it nearly looks like an ideal voltage.
Oh, that's right, because they're
source.
horizontal lines. Remember that the current source will look like a horizontal line.
Correct. So in fact, over here it looks almost ideal, and we refer to this region as saturation.
And the key is keeping a high VDS, so I guess there's going to be some tricks in doing that if I was an analog circuit designer.
That's right.
Okay.
Now, there's a transition region, as I mentioned earlier, at low VDS, that nice ideality goes away, and in fact the current does depend on VDS as well. So in this region, the current depends on both VGS and on VDS.
But let's see, if I look at this and I pretend, they go through zero, so if I pretend that these are lines, I could almost convince myself that for low VDSs, this looks like a resistor between DNS, and VGS just changes the value of the resistor.
That's right. And in fact, you will often hear this region referred to as the linear or triode region for that reason.
Okay, so I get it. So there's different regions of operation, and it's really set by the input voltage and then something about this VDS voltage that helps me determine what region I'm in. So now let me say two things. One is we didn't tell you anything about the physics of this. This is the wonder of the circuit abstraction. We can just move on in a minute and give you an equivalent circuit without really going into any of the details behind the semiconductor physics of this. And the second thing I'll tell you is that a lot of the fun in analog circuit design, as you move on to other courses, is in really the complexity and the elegance of how you set all of these VDSs and VGSs to get what you want. So we're going to do very simple examples here just to kind of give you a feel for it and nothing more. So building on what Vivek just taught us, if I take this transistor and I connect it to a drain resistor, and that's simply a resistor that's connected at one end to the drain and at the other end to some source voltage, VDD. This could be some 2 volts or 5 volts depending on how we set this up, VDD. And I'm going to take the source and connect it to the negative terminal. Often you'll see a ground here. Some people say, oh, this is grounded on the bottom. And in this configuration, I'd like to look at how I could put in an equivalent circuit for the MOSFET that'll come close to the behavior, because once we have that equivalent circuit, we maybe can use it in some other circuits and see what it does. So what I'm going to look at here is say, okay, let me stipulate that I could maintain a high VDS during my operation. Okay, let's just stipulate that that's somehow true. Okay, then just by looking at these curves, it stands to reason that I might be able to replace what's in here with simply a current source that's voltage controlled. So I've got my VGS voltage. Notice that this keys into what Vivek said, that because there's an insulator, there's no connection, there's no resistive path, there's an infinite resistance between the VGS and anything on this side, right? In here there's a wire, and so maybe you think something's going on here, but there's nothing. This VGS, no current, nothing connected to the left, flows any current. If I were to put a resistor and an ideal current voltage source, so make it a realistic voltage source, there would be no current, so Vin would equal the source voltage exactly. And so the current IDS is just going to be G times VGS.
So I see. Now what you've done is you've set it up by ensuring that I live in the right side of the curve, where I told you earlier that there's no drain voltage dependence. I now basically get an equation for the current that is completely independent of VDS.
That's right. That's what we've done. Now, of course, we're assuming that the person that designed this has either given us an input that will keep it biased at a high VDS, or we're going to play some tricks in an advanced class or an intermediate class. You'd understand how to play tricks so that VDS always stays where you want it to be. That's what's key. Notice something else we're going to come back to in a minute, which is if this is true, and let's pretend for a moment we're not connecting it to any load, okay, then our output here is going to be VDD minus the voltage drop across the resistor by KVL, right? VDD minus this resistor drop minus VDS equals 0. So what's this voltage drop? It's RD times this current, because it can only run down this way. So RD times G times VGS is going to be the drop on the resistor. And so in a minute we'll come back to this, but you'll see how by increasing the current here, we increase the voltage drop across here and lower the VDS. So that's a neat thing we'll come back to in a minute.
So if I understand that correctly, all you just told me is that the output voltage is just going to be VDD minus the voltage drop across here, which is just the current through here.
Yeah, exactly. Times the resistance.
Times the resistance.
Okay. So let's do an example.
All right. So the example we're going to do is a very simple amplifier. And I'm going to cheat a little. and the way I'm going to cheat is I'm going to meet that predicate that Michel gave us to start with. In other words, I'm going to design my circuit such that I guarantee it lives in that regime I want to live in, the so-called saturation regime. Okay? And the way I'm going to achieve that cheating is I'm going to pick the values of everything to ensure that that's the case. Now, in reality, of course, life is not so easy.
Sounds like academia, Vivek.
Yeah. So we'll go ahead and set that up. So here's how I'm going to cheat. I will first pick, this is the circuit I'm going to use, but I'm going to pick the values to ensure that I live in saturation. Now, when we talked about this, Michelle, what was the key to living in saturation?
Well, I think we want our VDS to be pretty large, right?
Right. We want VDS to be pretty large, and we want VGS to be large enough that the transistor is on.
That's right. We want to keep it on as well.
Right. So two constraints. Want to make sure VDS stays large and make sure that the transistor is on. The way to make VDS stay large is pick VDD and RD such that no matter what, no matter how much current is flowing through here, VDS stays large.
And by large, you mean a substantial fraction of VDD, I guess.
Correct.
For our purposes.
Yeah, that's right.
Okay.
I just want, in fact, if you look at the curves, basically what it means, it needs to be large relative to the gate voltage.
Okay.
Okay?
Okay.
So I've picked these values to ensure that that's the case. So just take it on faith that that's true. And I've given you a gain. Remember we said that this MOSFET can be represented as a voltage-controlled current source.
That's right.
Well, so I've given you what that function is. Okay?
Okay.
And that's this G term over here. And now to ensure that the transistor stays on no matter what, I'm going to apply a sinusoidal signal where the sinusoidal signal is defined as shown here graphically. But you'll notice something. The sinusoidal signal, I've got a DC offset to it. Specifically, the equation that I've used for the sinusoid is the applied voltage is 500 plus 40 times the cosine of 300t in microvolts.
So I guess what you're saying is, if this was an audio signal, pure tone at 300 t cosine, the amplitude is 40. You added this fake sort of DC shift up by half of what is that 0.5, so 500 microvolts. And that's what the cheating is going to happen, I guess.
Right. So remember, I told you earlier that the MOSFET is like a switch which turns off when the gate voltage is really low. Mm-hmm. By offsetting by 500 microvolts, so by half a volt, by offsetting by half a volt, by half a millivolt.
Half a millivolt.
I'm ensuring that the system stays on.
Yeah,
no matter
right,
what.
Right. Okay, let's show them how we did it. I think we're the only two enjoying this.
All right.
This insight.
So let's go ahead then and replace this transistor by the equivalent circuit that Michelle introduced before. So again, you'll notice that the gate terminal essentially behaves completely isolated. So there's no current through the gate. And then we've got this current source, voltage controlled current source shown over here. Okay, so what's the output? Well, the output voltage is just going to be VDD minus the voltage drop across the resistor. So that's VDD minus IDS times RD. Well, I know what IDS is. IDS is going to be the gain times VGS. So it's going to be VDD minus G RD VGS. So it's basically given me by output voltage is VDD minus G RD VDS. All right. Now, what is that? Well, I know what VDD is. It's 10 volts. I know what G is. G I've defined as 10. I know what RD is. RD is 1 kilo ohm, so that's 10 to the third. And I know what VGS is. That's this equation right over here. So I can plug it all in, and I can solve, and I can get the output voltage. And you'll notice something. The output voltage is now 5 minus 0.4 cosine 300t. So a couple of things to note. One, there's a plus sign here, there's a minus sign here, which means when the input is going down, the output will be going up, and vice versa. So it's an amplifier, but it's inverting.
It's inverting.
Okay? And further, what you'll note is the frequencies in all stayed the same. So this is a real amplifier.
That's right. And I guess because obviously we're using linear components, so
right.
Our frequencies just went straight through.
Right. Now, it is worth noting that the ear cannot tell the difference between inverting and non-inverting amplifiers. So a lot of the amplifiers that you'll buy commercially will often be inverting amplifiers, but the ear doesn't hear the difference.
Oh, that's interesting. But I guess that in the end, what the trick was that you keep your VDS at a sort of pinned right here, right at some fixed DC value, and then this small wiggle around it.
Correct.
So this is what we said about cheating. We essentially ensure that we always keep it at a VDS that's large enough that this model makes sense.
Correct.
So two quick things. One is, some time ago we talked about how models sometimes only work in certain regimes. This is an example. This would only work because we picked this input so that we can use this model, and it may very well just not work that way for other inputs.
Right. So, and remember, the regimes we picked as we ensured that it was not in cutoff. In other words, the switch was not off, and we ensured that it was in saturation, so at high VDS.
Right. Another simple detail is that Vs equals VGS because there's no current through this RS. This RS really doesn't do anything in this example because there's no current going down this branch. And the third thing I'll say is that the beauty of, I said this before, but the beauty of all this is when you get into your intermediate classes and you learn how to bias these things, add additional resistors and transistors to maintain transistors in the operational regime you want it for a useful application. And that's a lot of analog circuit design. It's really a lot of fun. And I encourage you, if this sort of whetted your appetite, this very simple sort of baby example, really go in and take your analog circuit design courses, because it's quite a lot of fun. Okay. Now, let's take another example. Let's see another use for this. Now, Vivek said the MOSFET was the sort of industrially most important transistor, and the real reason for that is that it's taken over since the mid-'80s, early '80s. It's steadily been taking over the digital market till these days. Really, all digital computation is done with MOSFETs. There's some reasons for that, but let's just take a look at how you could create a simple logic gate that you might have seen in some of your other classes. And this one's not going to be particularly great. This is actually a fairly poor logic gate, but it sort of highlights the point, the fundamental way of looking at this. So let's look at almost the same circuit we saw before. Okay, and in the last slide we were interested in this in the context of analog circuit design, right? We're looking at an amplifier, we're putting in some signals, we want to get a signal out, maybe use it for a speaker or whatnot. Here we're going to look at it strictly kind of in a digital domain. And so I'm going to ask you some very basic questions, and it's worth thinking about them, and we'll tee off with Vivek. So let's say I have a VDD, and the bottom part is in fact grounded, and I'm going to stipulate that whatever VDD is, let's call it 2 volts, that's going to be my logic 1. So anytime the output has a VDD, a value of VDD, or something very close to it, I'm going to assume that the next circuit past me understands that as a logic 1. We're building digital circuits. And if I have a very low voltage either in or out that's close to ground, in other words, the voltage difference at V out between plus and minus, or at V in between plus and minus, is very, very small, close to 0, we will assume that the system understands it as a logic 0. So now take a look at something very cool as a consequence of how this works. If I put in a very, very low input voltage, let's say I put in 0, so identically 0 is what goes on here. What states the transistor in, Vic?
Okay, well, I told you earlier that when there's a low gate voltage on that transistor, it's going to be off. So that transistor will be off. In other words, no current will flow through it.
Right, no current's flowing through. So this IDS is 0. This is doing nothing. It's as though there were an open between D and S. If that's the case, then what's the current going through RD?
Assuming that there's no load on the output, there'll be no current going through RD, which, let me guess, that then means the output is at VDD.
That's right. There's no voltage drop here, so by KVL, V out equals VDD.
Cool. So what this means is when my input was 0, my output is 1, because I went in with 0 in, and I came out with VDD out.
That's right, and here's what this shows, right? So for some values, even as Vn gets a little bit higher than 0, because it takes some amount of voltage to really fully turn it on, the output's going to stay at logic 1 for quite some time. Another point that you brought out that's really neat is you said as long as there's no load. And the cool thing about MOSFETs, as you pointed out to us at the beginning, is that there's no resistive path through the gate. So if there's a MOSFET at the output, it actually doesn't load this very much. And that's one of the fundamental reasons why MOSFETs have been so instrumental, that I can stack them and they don't influence each other's inputs, each other's outputs with their inputs. You'll run into this in your digital classes. We don't have to belabor it, but it's a very cool little detail. Okay, now let's look at the other case. Let's say I put in a really big VN. What's a really big VN? Well, the digital circuit before this could really only put out VDD as its biggest value. So let's say we put in VDD here. Well, now we know VGS is going to be very large.
Right.
So what do we know about the equivalent through here?
Well, if VGS is going to be large, that transistor operates like a voltage-controlled current source and will pull a lot of current.
That's right. So now it's going to run a whole mess of current down here. Don't worry about the numbers for now. It's just a large number. And that large number times this resistance is what? The voltage across the resistor.
Right. So there's basically, I understand. So what you're saying is there's going to be a really large current, which means there's a large voltage drop. So it effectively is like pulling the output to ground. You can think of it as a voltage divider, essentially, where RD is some value, but the transistor acts like a really low resistance.
That's exactly right. And so V out drops very low. And again, it's very cool because you put in a very big voltage, a logic 1, and you get a very small voltage, a logic 0. So this is an inverter. It's a logical inverter. It's your first baby inverter. You could actually compute something interesting with this.
Cool. Now, of course, what we haven't really talked about is what happens in the transition, which you see over here in the transition region of the curve. But we're not going to talk about that right now.
Yeah, although I'm going to guess it probably looks kind of like the amplifier on the slide before, but
That's right.
But we'll skip that for now. Those of you that really like this stuff, feel free to come and ask us. Vivek and I love talking about this for hours on end. So we can see if you can figure out why we think that.
Now, we just put some sort of industrial context to this. This type of inverter is not really used today for a bunch of reasons, but this was an inverter that was used in this form or in a slightly analogous form in the late 1970s, early 1980s time frame.
Right, and we'll give a hint to those that like looking ahead and doing extra credit work. The key is that you don't want a resistor there because the resistor will burn power that you don't really need burnt, and so the modern FET inverters that are based on CMOS or complementary actually put a slightly different transistor there to get the same functionality. But we'll skip that for now. Really, we just want to introduce you to some basics.
Okay. So having built the inverter, we can build more complicated gates. And one of the gates we can build is a NAND gate, which is an inverted AND gate. Let's start out by defining the function, just for those of you who don't remember it. For a 2-input NAND gate, the function is basically the following. It'll produce an output of 1 for all situations unless A and B are 1, in which case it produces a 0.
Okay, so I guess it's NAND stands for inverted AND. So
Right.
an AND would be if A is 1 and B is 1, then you get a 1. In the other cases, you get 0, and this is just the flipped version of that.
Correct. So that's basically our truth table shown over here. And you see the truth table says you only get a 0 if both outputs are 1. Now you can see pretty easily how to build that. If I connect two transistors in series, the only time these two transistors would turn on would be if both A and B were high.
In other words, if both the gate to ground or gate source voltage on this transistor and that transistor are high, the transistors are on, they're both running current, that current goes through this resistor up here and drops V out.
Right, so remember, it's pretty simple. These two are in series with each other. The only way for current to flow is if both of them are on. If only one of them is on, the other one will block current.
So the whole game here is what condition gives you current through this resistor, and we know that anytime there's current through this resistor, there's a large voltage drop, and so this drops to 0.
Right.
Got it. And there's only one condition that does that.
Right, and so what we have then is the truth table will produce if any of the other situations exist, either A or B or both are off, the output will be high because you're essentially getting to VDD through the resistor.
Right, there's no current through the resistor.
Right, there's no current through the resistor, and only when both are on do you get this.
All right, let's take another look at another one. So let's say I put the transistors side by side instead of one after the other. So in this case, you get something called a NOR. And again, let's look at the truth table. Why is it that when both of them are 0, you get a 1? That seems very counterintuitive. But I see it's a NOR, so it's an inversion of an OR. So what's an OR?
All right, so an OR gate will produce a high when either or both of its inputs are high.
So if either A or B is 1 or both, I would have gotten a 1. So there would have been 1s here instead of 0s. But since this is an inversion, so it's a NOR, I just flip it. So this is 0, 0, 0, and a 1 here. Okay.
Right. So a NOR basically is a gate which will only produce a 1 when both its inputs are 0.
Are off. And that makes sense, right? Because if both of them are off, then the same thing happens as we spoke to before. There's no current through here, and VDD just gets transferred to V out, or rather, there's no voltage drop across the resistor. So V out equals VDD. I get a 1. But in any time one of them turns on, it doesn't matter if one of them does or both of them do, it immediately runs current through the resistor, pulling down V out very close to 0.
Okay, that makes sense. So it looks like we've been able to do NOR gates, NAND gates, and inverters. We basically have everything we need to start doing Boolean logic.
That's true. If you remember from some of your classes, and if you don't, you'll probably take them soon. In fact, with these gates, and in fact a subset of these gates, you can, in theory anyway, build any logical function, any combinational logic function you might be interested in. So it's pretty powerful that you even know how to do this with these simple transistors. I think it's a good point to stop. This was meant really just as a little intro to what kind of things you can do with MOSFETs. Fair enough?
Sounds good.
All right, we'll catch you in the next module.